We're being asked to find the average rate of change of a function. Let's go ahead and do it. So there's a formula for the average rate of change. It's f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. So let's go ahead and do it in pieces. So first let's work out f of 3. So f of 3, well, we just replace all of the x's with 3's. So we get 3 squared plus 4 times 3. 3 squared is 9, and 4 times 3 is 12. So we get 9 plus 12, which is equal to 21. Now let's work out f of 1. X sub 1 is our 1. So we have 1 squared plus 4 times 1, which is 1 plus 4, which is equal to 5. And now let's go ahead and use the formula. So this is equal to, let's see, x2 was 3. So it's f of 3 minus f of 1 divided by 3 minus 1. F of 3 is 21, f of 1 is 5, and 3 minus 1 is 2. So we get 16 over 2, which is equal to 8. And that's how you find the average rate of change. Hey everyone, in this video we're going to talk about some really important graphs in mathematics that everyone should know. So common graphs. And the idea is that you just have these shapes memorized. It's so useful to know what these shapes look like for higher level math. So a good one to know, the first one is called constant graph. So constant graph. Okay, and this one looks like f of x equal to a constant c. So like f of x equals 2, f of x equals 3, etc. If you recall, y is equal to f of x. So these are just horizontal lines, right? So like y equals 2, y equals 3. So I'll just start like this. Here's c, and we have a horizontal line. So that's it. So that's just a common graph that you should know. So whenever it's f of x equal to a number, it's just a horizontal line. That's the first one. The next one's really important for higher level math specifically. It's called the identity function. By the way, I could have written constant function. I don't know why I wrote constant graph, but same thing. The identity function. So this one is f of x equal to x. So whatever x is, so is y. So like if x is 2, y is 2. So you end up with a diagonal line like this, right? So that's the graph of f of x equals x. Right, that's the graph of f of x equals x. Another one that's really important, and again, it's just good to have it memorized, is what's called the standard quadratic. So standard quadratic, okay, standard quadratic. That's f of x equals x squared, okay? This is also called a parabola, okay? And it looks like a u. You want to just memorize it, okay? It looks like a u, okay? It looks like a u. And say, well, why does it look like a u? Well, you could plug in numbers to convince yourself, right? If you plug in 2, you get 4. If you plug in 1, you get 1. So you can convince yourself that it does indeed have this shape. So here's 1, and then here's 2, and then here's 4. So it gets big really quick, right? It gets big pretty quick. And if you plug in a negative 2, you're going to get a positive 4 because it's being squared. Let's check this out. You get negative 2 squared, which is 4. So you'd be, again, way up here. So you do get the same thing on both sides. This is an example of what's called an even function. If you remember from a previous video, it's symmetric across the y-axis, so it's an even function. Then you have what's called the square root function. This one's super important. Square root function. So f of x equals the square root of x. Okay, so that's the y-axis, that's the x-axis. And this one looks like that. I always think like a dying finger. That sounds really weird, but it looks like that. It goes up forever, right? So it keeps going up really, really slowly. For example, if you plug in 4, you get the square root of 4, which is 2. And if you go all the way out to 100, right? So if you plug in x 100, x equals 100, you only get 10. So when x is 100, you're still only at 10. So it grows very, 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 very very slowly. Right? It's called the square root function. A few more important ones. The next one's called the standard cubic function. And this one's just f of x equals x cubed. Okay, very useful to know what this looks like, especially when you're studying polynomials, which we'll study later. It looks kind of like this. Now, it flattens out at 0. Actually, at 0, it's supposed to be completely flat. Like, it's completely horizontal at that moment. At 0, it's supposed to be completely horizontal. So it's pretty much impossible to draw perfectly, but that's called the standard cubic. Then you have the cube root function. Okay, cube root function. And it takes time to memorize these. You're not supposed to memorize them all at once. I mean, it's better to. If you can do that, that's great. This one kind of looks like a cubic function, but it's like sideways. So at 0, it's actually supposed to be vertical. Like specifically at 0, it's actually vertical. And this is f of x equals the cube root of x. Cube root of x. And the very last one that's important to know is my favorite one. It's the absolute value function. Absolute value function. So f of x equals the absolute value of x. And this one looks like a v. So it looks like this. Absolute value of x, it's a v. So it's a v. It's a v. So the absolute value function is a v. Whereas x squared is a u. So that was just a quick video just to show you the common graphs that you should just eventually memorize. Hope that made sense. In this video, we're going to look at some basic transformations of graphs. So we'll start by letting c be a positive number and y be equal to f of x. So the first few transformations were we're going to look at involve vertical and horizontal shifts. The first one is f of x plus c. This means we shift up by c units. So we shift the graph of f of f up c units. Then we have f of x minus c. This one's down c units. And then f of x plus c. So we're adding c to the x. This one's, you think it's right, but no, it's backwards. It's left c units. And then the last one we're going to look at for now is minus c. So this is right c units. These feel backwards. That's how I memorize them. Whenever you add to the x, you think it's right, but no, it's left. Whenever you subtract from the x, you think it's left, but no, it's right. So it's a little bit backwards. Let's look at a bunch of simple examples. So let's say we had y equals x squared plus 3. So you want to think of this as your f of x, right? This is your f of x. And you're adding 3 to it. So x squared looks like this. It's a standard quadratic. Right? This is the graph of x squared right here. This is x squared. And it starts at 0, 0. So basically we're adding 3, so we're taking each y value and shifting it up by 3. So we're taking the entire graph and going up by 3 units. So from 0, we just go up 3. 1, 2, 3. And you put a dot, and then you just draw the u. That's it. That's this graph right here. Let's look at another example. Say we had f of x equals the square root of x plus 2. In this case, our base function, or our core function, is y equals the square root of x. So it looks like this. That's y equals the square root of x. And we're adding 2 to the x. So you think it's right, but no, it's left. So we take this whole picture and we just go left 2. And there it is. So this would be this function here. So in this case, we went up 3. In this case, we went left 2. Look at another example. Do it down over here. Say we have f of x equals the absolute value of x minus 2. In this case, our base function or our core function, is the absolute value function, which looks like a v. And this means we're going down 2 because we're subtracting 2 from the entire function, right? So we just take this v, and from the middle we go down 2. So 1, 2, boom, and we draw the v. And that's it. Let's do maybe one more. Say we had f of x equals, I don't know, let's see, x plus 3 quantity squared. In this case, we were going left 3 because we're adding to the x, so it's backwards, and the base function or the core function is x squared. So we start with this one, and then we just take the whole graph and go left 3. So 1, 2, 3, and there's our u. Oh, one more. We're going kind of fast, but it's good to see lots of examples. F of x equals, let's do square root of x minus 2. So in this case, you're subtracting from the x, so it's backwards, so it's right 2. So we take our square root function. There's our u. Oh, one more. We're going kind of fast, but it's good to see lots of examples. F of x equals, let's do square root of x minus 2. So in this case, you're subtracting from the x, so it's backwards, so it's right 2. So we take our square root function. There's our square root of x. And we take this entire graph and we go right 2. So 1, 2, boom, there it is, and there's that graph there. So to recap what we've done, because we went kind of fast, in the first example here, x squared, that was our u, and we went up by 3. So we took the whole graph starting at 0, and we just went up by 3. We got our graph right there. Beautiful stuff. Okay. The next example was the square root function. When we add 2 to the x, it's backwards, so it's left 2. So we took our square root function, and we shifted it left by 2. And the next example we had was the absolute value of x minus 2. So we started with the absolute value of x. That was our core function. We subtracted 2 from the entire function, so we went down 2. The next example we had was x squared. We add to the x, so it's backwards, so it's left 3. So we took the whole picture, and we went left 3. And the last example we saw was another square root function. We subtracted from the 2, so it's backwards, so it's right 2. I hope that made sense. Hey everyone, in this video we're going to talk about reflections. So reflections of graphs, really basic. basic ones. So say we have a function y equal to f of x. And so there's basically two transformations of graphs we'll be looking at. So the first one is if you have a negative sign in front of your y value, so in front of f of x. In this case, you reflect the graph, reflect across x-axis. So a really easy, cheesy way to memorize it is if the negative is in front of the y, you reflect across the x. That's how I memorize it. The other one is if you have a negative sign in front of the x. In this case, you reflect across the y-axis. So if you have a negative sign in front of the x, you reflect across the y. So wherever you have the negative sign, you reflect across the other one. So negative in front of the y, because y is equal to f of x. So negative in front of the y, reflect across the x. Negative in front of the x, reflect across the y. So again, negative in front of the y, reflect across the x. Negative in front of the x, reflect across the y. It's fun. Let's do a couple examples of graphs. So sketch. That's a really big C. Sketch. And I don't know. Let's do f of x equals, call it part A. Let's go down the alphabet a little bit. So square root of negative x. Okay, so solution. So how would you graph this if you were doing it? By hand. Well, first you graph the square root function. That's your core function, your base function, your mother function. So the square root of x looks like this. Boom, that's the square root of x. I won't call it f, let's call it g. So g of x is the square root of x. So this is just from memory. So you have this memorized. Then you see the negative in front of the x, so you reflect across the y-axis. So we take this graph and we just reflect it across the y-axis. So what would that look like? It would just look like this dotted line here, right? Just a reflection across the y-axis. So I'll draw it over here. There's the y-axis. There's the x-axis, so x and y, and boom, there it is. There's the reflection across the x-axis. So this is the graph of square root negative x. Let's do one more, b. Actually, two more, c. Let's look at f of x equals negative x squared, and let's look at f of x equals negative absolute value of x. So in the first case, we have an x squared, so we have the standard quadratic function. It's also called a parabola. So the core function or the base function is a u. Looks like this. Right, so this is the y-axis, this is the x-axis, and that's the graph of g of x equals x squared. In this example over here, part C, our base function or our core function is the absolute value function. So the absolute value function looks like a v. Just think v for value. Right? Easy, cheap trick to memorize it. V for value. Okay, so now let's do these problems. So in part B, we have a negative in front of the y value, right? So we reflect across the x-axis. So all you do is you take this graph and you just flip it down across the x-axis. So it would look like this dotted line here. So I'll draw it again on its own over here. It's just an upside down u, right? Because it's reflected across the x-axis. So that would be the answer to part B. In this case here, it would just be an upside down v. So it would look like this dotted line here. So I'll draw it over here. It's just an upside down v in this case. In the first case, it's an upside down u. And that would be the answer to this one. So if you have negatives in front of the actual function values, in front of the y values, you just reflect across the x-axis. Whereas up here, we had a negative in front of the x value, so we reflected across the y-axis. Hope that made sense. Graph f of x equals the quantity x plus 2 squared minus 4. So in In this video, we're going to graph this function. And so we'll start by looking at the base function or the core function or the parent function. That would be y equals x squared. So when you see this problem, you want to think about this graph here. And what we're doing is we're shifting it left and right, up or down. So whenever you add a number to the x, it's backwards. You think it's right, but no, it's left. And whenever you subtract a number from the entire function, it's down, so down 4. So for example, if instead it was x minus 2 quantity squared, this would be right 2. X plus 2 was left 2. If it was x squared plus 2, like if the plus 2 was on the outside, it would be up 2. So if a number on the outside of the function, if it's negative, you go down. If it's positive, you go up. But when it's next to the x, it's always backwards. All right, good stuff. So now we'll draw our y-axis, and we'll draw our x-axis. So x, y. And then from the origin, we're going to go left 2 and down 4. So 1, 2, 1, 2, 3, 4, and we'll put a dot. And now we're just supposed to draw the u. The problem is it's going to cross the x and y axes. So we should go ahead now and find the x and y intercepts. So to find the y-intercept, you always plug in 0 for x. So f of 0 is equal to parentheses 0 plus 2 squared minus 4. So 2 squared is 4. Oh, how convenient. 4 minus 4 is 0. Good stuff. So that was a coincidence. So here it's going to cross here at 0, 0. Now we have to find the x-intercepts. Well, apparently we've already found one of them. So to find the x-intercepts, you take the entire thing, right? You take y, and you set it equal to 0. So x plus 2 quantity squared minus 4 equals 0. To solve this for x, you add the 4 to both sides. So plus 4 plus 4. Boom. So we have x plus 2 quantity squared equals 4. And to get rid of the 2, you just take the square root of both sides. So square root. So you have x plus 2 equals, now when you take the square root and you have a variable squared, you always put a plus or minus, so plus or minus 2. And finally, we subtract the 2. So we end up with x equals negative 2 plus or minus 2. Okay, I did that kind of fast. So when you're finding x-intercepts, you take the entire thing, okay, the whole thing, and you just set it equal to 0. And then we just go through the math. We added the 4. We took the square root of both sides. We got a plus or y-intercepts. So to find the y-intercept, you always plug in 0 for x. So f of 0 is equal to parentheses 0 plus 2 squared minus 4. So 2 squared is 4. Oh, how convenient. 4 minus 4is 0. Good stuff. So that was a coincidence. So here it's going to cross here at 0, 0. Now we have to find the x-intercepts. Well, apparently we've already found one of them. So to find the x-intercepts, you take the entire thing, right? You take y, and you set it equal to 0. So x plus 2 quantity squared
tienes 10 manzanas y quieres repartirlas entre 2 personas. A cada una le tocan 5 manzanas. Eso es una ¿Conoces el triángulo de Sierpinski? Nació de una regla simple. Tomas un triángulo, conectas los puntos medios de cada lado y vacías el triángulo central. Repites este proceso infinitas veces en cada triángulo que queda. Pero aquí viene lo extraordinario. Tu dimensión es 1.585, ni 1 ni 2, dimensión fraccionaria. ¿Pero por qué? Porque la dimensión mide cómo crece una figura al escalarla. Si duplicas una línea, obtienes 2 copias. Si duplicas un cuadro, obtienes 4 copias. Si duplicas el triángulo de Sierpinski, obtienes exactamente 3 copias de sí mismo, ni 2 ni 4, algo intermedio. Y ese intermedio matemáticamente da 1.585. No es una línea, no es un plano, es algo que existe entre ambos. ¿Conoces el triángulo de Sierpinski? Nació de una regla simple. Tomas un triángulo, conectas los puntos medios de cada lado y vacías el triángulo central. Una división. Pero ahora intenta repartir esas mismas 10 manzanas. Repites este proceso infinitas veces en cada triángulo que queda. Pero aquí viene lo extraordinario. Tu dimensión es 1.585, ni 1 ni 2, dimensión fraccionaria. ¿Pero por qué? Porque la dimensión mide cómo crece una figura. ¿Conoces esta ecuación? Se llama identidad de Euler y es considerada la ecuación más bella de las matemáticas. ¿Pero por qué? Porque une 5 números que cambiaron la historia. La base del crecimiento natural. Sin él no existiría el cálculo moderno. Y la unidad imaginaria, el número que los matemáticos consideraban imposible hasta que resultó ser indispensable. Pi, la razón que gobierna todo círculo del universo, presente en la naturaleza mucho antes de que alguien lo descubriera. 1, el primer número, el origen de todo sistema de conteo. Y 0, quizás el descubrimiento más revolucionario de la humanidad, porque entender la nada como número lo cambió todo. En efecto, Esta ecuación no es decorativa, se usa para describir ondas eléctricas y señales de audio, para calcular rotaciones en gráficos 3D y en mecánica cuántica. Básicamente, cada vez que algo oscila o rota en la naturaleza, Euler aparece. ¿Conoces esta ecuación? Se llama identidad de Euler y es considerada al escalarla. Si duplicas una línea, obtienes dos copias. Si duplicas un cuadro, obtienes cuatro copias. Si duplicas el considerada. Mira este fractal. Nació accidentalmente del método de Newton, una técnica para encontrar las raíces de una ecuación. Por ejemplo, x al cuadrado menos 2 igual a 0. Si resolvemos la ecuación directamente, obtenemos dos soluciones. X igual a más menos raíz de 2, es decir, x es aproximadamente más menos 1.4142. Pero en este ejemplo vamos a seguir la raíz positiva. Newton creó una fórmula iterativa. Como contexto, iterar significa repetir el mismo cálculo una y otra vez, usando siempre el resultado anterior. Volviendo, para esta ecuación su derivada es 2x. Entonces, la fórmula queda así. Si empezamos con x sub 0 igual a 1, la primera iteración produce esto. X sub 1 igual a 1.5. Luego repetimos el proceso con este valor y nos da x sub 2 aproximado 1.416. Y otra vez repetimos y nos da 1.414. Cada iteración corrige el resultado anterior, acercándose cada vez más a raíz de 2, que es aproximadamente 1.4142. Pero eso ocurre en una sola dimensión, sobre la recta numérica. Cuando aplicas el método en el plano complejo, en dos dimensiones, millones de puntos distintos empiezan a viajar hacia raíces diferentes. Entonces, coloreas cada punto según la raíz a la que llega y aparecen regiones de color. Y esos bordes caóticos forman el fractal de Newton. Mira este fractal. Nació accidentalmente del método. ¿Qué es el efecto mariposa? Es un fenómeno de los sistemas caóticos donde pequeñas variaciones iniciales producen ¿Conoces el conjunto de Julia? Su fórmula es casi idéntica a la de Mandelbrot, pero cambia cómo se usa el número complejo, y ese pequeño cambio genera algo completamente distinto, no un fractal único, sino infinitos fractales posibles. Cada valor que elijas genera su propio universo fractal. Algunas son figuras simétricas y conectadas, otras se fragmentan en miles de islas separadas, y todos viven en el plano complejo, ese plano de dos dimensiones. Y aquí viene lo más curioso. Pequeños cambios en ese valor generan formas radicalmente diferentes, cada uno con su propia personalidad matemática. Pero este conjunto nació en 1918, cuando el matemático francés Gaston Julia perdió la nariz en la Primera Guerra Mundial, y durante su recuperación en el hospital, sin computadoras, sin calculadoras, desarrolló a mano parte de una de las teorías más hermosas de las matemáticas. Julia murió sin ver sus fractales dibujados. Las computadoras llegaron décadas después de su muerte. Desarrolló mundos infinitos que nunca pudo ver. ¿Conoces el conjunto de Julia? Su fórmula es casi idéntica a la de Mandelbrot, pero cambia cómo se usa el número complejo, y ese pequeño cambio genera algo completamente distinto, no un fractal único, sino infinitos fractales. ¿Sabías que Isaac Newton dedicó más tiempo a la alquimia que a las matemáticas? Pero, ¿qué es la alquimia? ¿Para qué sirven los fractales? Su primera utilidad es matemática. Ejemplo, el conjunto de Mandelbrot y el Burning Ship viven en el plano complejo y ayudan a estudiar sistemas dinámicos donde pequeñas variaciones cambian completamente el resultado. comportamientos similares a los del clima o mercados financieros, sistemas que al iterarse pueden volverse caóticos e impredecibles. Y lo que hace únicos a muchos fractales es esto: su dimensión no es entera. Una línea es una dimensión, un plano es dos dimensiones, pero algunos fractales viven entre medias. El triángulo de Sierpinski tiene una dimensión aproximada de 1.58. No es una línea ni un plano, es algo intermedio que la geometría clásica no podía describir. Y esa dimensión fraccionaria resultó ser increíblemente útil. En telecomunicaciones, las antenas fractales captan múltiples frecuencias usando muy poco espacio. En gráficos 3D generan montañas y terrenos con ecuaciones iteradas. Y en medicina ayudan a modelar pulmones y vasos sanguíneos con gran precisión. ¿Para qué sirven los fractales? Su primera utilidad es matemática. Ejemplo, el conjunto. ¿Qué es un fractal? Es una figura. ¿Qué es el burning ship? Es un fractal que nació de modificar una sola regla del conjunto de Mandelbrot. En lugar de calcular z al cuadrado más c directamente, primero tomas el valor absoluto de la parte real e imaginaria de z y luego elevas al cuadrado y sumas c. Ese pequeño cambio lo transforma todo. La figura deja de ser orgánica para volverse agresiva, con bordes afilados que forman una estructura similar a un barco en llamas vista desde arriba. Por eso su nombre, Burning Ship. Su gráfica vive en el plano de los números complejos con eje real e imaginario, una fórmula casi idéntica a Mandelbrot pero con un resultado completamente distinto. ¿Qué es el Burning Ship? Es un fractal que nació de modificar una sola regla del conjunto de Mandelbrot. En lugar de... Seguro viste esta ecuación al... Mira esta fórmula. Ramanujan la soñó literalmente. Afirmaba que la diosa Namahiri se la dictaba mientras dormía. Se despertaba, la anotaba y era correcta. Sin demostración, sin proceso, sin explicación. Es una serie infinita que calcula pi. Empieza en k igual a 0 y suma infinitos términos. Cada uno. ¿Qué es el conjunto de Mandelbrot? Es uno de los objetos más complejos de las matemáticas, pero nace de una fórmula de solo dos símbolos. El juego es simple. Z siempre empieza en 0. Eliges un número C, calculas y el resultado se convierte en la nueva Z. Ahora repites esto infinitas veces. Por ejemplo, si C es igual a 1, el resultado crece sin control. 1, 2, 5, 26. Este número escapa al infinito. Pero si C es igual a 0, el resultado siempre es 0. Se mantiene atrapado para siempre. Al graficar esos puntos, surge una figura de complejidad infinita, un fractal donde, sin importar cuánto te acerques, el detalle nunca termina. ¿Qué es el conjunto de Mandelbrot? Es uno de los objetos más complejos de las matemáticas, pero nace de una fórmula de solo dos símbolos. El juego es simple. Z siempre empieza en 0. ¿Cómo nacieron los hipercomplejos? Reales, complejos, cuaterniones, octoniones. ¿Cómo llegamos hasta ahí? Todo empezó con un problema. ¿Qué número multiplicado por sí mismo da negativo? Ningún. ¿Cómo nacieron las hiperoperaciones? Suma, multiplicación, potencia y después ¿qué? Tetración, pentación, hexación y así sin fin. Pero, ¿cómo llegamos hasta ahí? Los matemáticos notaron un patrón. Sumar repetidas veces es multiplicar. Multiplicar repetidas veces es elevar. Entonces, elevar repetidas veces debía ser algo nuevo. La tetración. En 1928, Wilhelm Archmann formalizó esta idea, construyendo una función que crecía más rápido que cualquier operación conocida hasta ese momento. Después, Reuben Goldstein En 1947 organizó toda esa secuencia en un sistema y la llamó hiperoperaciones. Como ves, no nacieron para resolver un problema del mundo real, nacieron porque los matemáticos se preguntaron qué había más allá y no pudieron parar. ¿Cómo nacieron las hiperoperaciones? Suma, multiplicación, ¿Conoces esta ecuación? Es el último teorema de Fermat y estuvo sin resolverse durante 358 años. Dice esto: no importa qué bases enteras positivas elijas para x, y y z, si el exponente n es mayor que 2, la ecuación nunca se cumple. Nunca. Fermat la escribió en 1637 en el margen de un libro y anotó que tenía una demostración. Nunca la escribió, pero en 1993 Andrew Wiles la anunció ante el mundo, después de 7 años trabajando en secreto. Pero había un error. Junto a Richard Taylor lo corrigió y en 1995 se publicó la demostración definitiva. Este teorema no tiene aplicaciones directas en ingeniería o física, su valor es otro. Demostró que problemas simples pueden esconder matemáticas profundísimas. ¿Conoces esta ecuación? Es el último teorema de Fermat y estuvo sin resolverse durante 350.
Minus 4 equals 0. To solve this for x, you add the 4 to both sides. So plus 4. Boom. So we have x plus 2 quantity squared equals 4. And to get rid of the 2, you just take the square root of both sides. So square root, square root. So you have x plus 2 equals, now when you take the square root and you have a variable squared, you always put a plus or minus, so plus or minus 2. And finally, we subtract the 2. So we end up with x equals negative 2 plus or minus 2. Okay, I did that kind of fast. So when you're finding x-intercepts, you take the entire thing, okay, the whole thing, and you just set it equal to 0. And then we just go through the math. We added the 4, we took the square root of both sides, we got plus or minus when we did that. And now we have two cases. We have x equals negative 2 plus 2, so that's 0. And the other one is negative 2 minus 2, that's negative 4. So that would be over here. So these red dots are the x-intercepts. The yellow one is the vertex. And now we just connect the dots, right? All we do now is connect the dots and make our super awesome graph. So it's a U shape, so there we go. It's pretty good. And that's the graph of our function. I hope this video has been helpful. That's it. So you have to sketch the absolute value of x minus 2 plus 3. So in this problem, the first thing you want to do is look at the absolute value of x. That looks like this. It's a v. Okay, and then when you're subtracting 2 from the x, that tells you you're going to be shifting the graph right by 2. You'll be shifting this graph right by 2. And when you add to the actual function, you're going to go up 3. So let's draw our final answer here. So there's the x-axis, there's the y-axis. Okay, so we're taking this picture here, and we're going to move it to the right 2 and up 3. So 1, 2, 1, 2, 3. Put a dot and draw your little v. And there it is. Almost done. We crossed the y-axis, so we have to find the y-intercept. In order to find the y-intercept, you plug in 0 for your x. So f of 0 is the absolute value of 0 minus 2 plus 3. So you get the absolute value of minus 2 plus 3. 2 plus 3 is 5. So that's it. That number right there is 5. So we have to sketch the absolute value of x minus 2 plus 3. So in this problem, the first thing you want to do is look at the absolute value of x. That looks like this. It's a v. Okay, and then when you're subtracting 2 from the x, that tells you you're going to be shifting the graph right by 2. You'll be shifting this graph right by 2. And when you add to the actual function, you're going to right by 2 from the x. That's a v. Okay, and then when you're subtracting 2 from the x, this graph, the x-axis, and we're going to move put almost done. We crossed the y-axis, so we have to find the y-intercept. In order to find the y-intercept, you plug in 0 for your x. So f of 0 is the absolute value of 0 minus 2 plus 3. So you get the absolute value of minus 2 plus 3. 2 plus 3 is 5. So that's it. That number right there is 5. Graph the absolute value of x plus 2 minus 1. Let's go ahead and work this out. the first thing I do when I do these is I think about which way the absolute value function is being shifted. So we're adding 2 to the x, so you go left 2. And we're subtracting 1 from the entire absolute value, so we're going down 1. 2 and down 1, so left 2 and down 1. So let's carefully do that over here. So this is the y-axis. So we're going to move this little table. You set x equal to 0. So y is equal to 1. So when x is 0, right, we plugged in 0, y is equal to 1. So the y-intercept is 0, comma 1. So I'm going to go back to the picture and draw that in. So you go right 0 and up 1. Boom, there it is. Now let's go ahead and find the x-intercepts. Again, to find any intercept, you set the other one equal to 0. So in this case, we set y equal to 0. So we have 0 is equal to the absolute value of x plus 2 minus 1. If we add 1 to both sides, we get 1 is equal to the absolute value of x plus 2. For clarity, I'm going to write this as the absolute value of x plus 2 is equal to 1. Whenever you have an absolute value and you want to get rid of it, you have to put a plus or a minus. So here you get x plus 2 equals 1, or x plus 2 equals negative 1. Then you subtract subtract 2, so you get x equals negative 1, and you subtract 2 here, and so you get x equals negative 3. So let me come up here where there's more room, and it looks like when y is 0, x is negative 1, so we get negative 1, 0. And when y is 0, x is negative 3, so we get negative 3, 0. So these guys here are the x-intercepts. So we have one here, that's negative 1, 0, and the other one is right here, negative 3, 0. And now we can finish our graph. So all we have to do now is connect the dots and make it look like a V. It's very hard to draw a straight line. Maybe that's the hardest part of the problem. So there is our beautiful absolute value function, the absolute value of x plus 2 minus 1. And that is the final answer. I hope this video made sense.